The Solar System. Planets and Constellations. Introduction to the Solar System and Cosmology. The cosmos, in its boundless expanse, holds within its intricate tapestry countless wonders, and among the most immediate and profoundly influential for humanity is our very own solar system. This celestial neighborhood, a gravitational ballet of planets, dwarf planets, moons, asteroids, comets, and dust, all bound by the immense gravitational pull of our central star, the Sun, represents a microcosm of the grander universe. Understanding its origins, its components, and its dynamics is not merely an academic pursuit, but a fundamental quest to comprehend our place within the vast cosmic ocean. This inaugural part of our lecture will lay the foundational stones, introducing the solar system's definition, its cosmic address within the Milky Way galaxy, the historical evolution of our understanding of its structure, the prevailing theories of its formation, and a preliminary overview of its diverse constituents. We will also touch upon the staggering scales involved, and underscore the enduring relevance of studying this remarkable corner of the universe. At its most fundamental, the solar system is defined as the Sun and all the celestial bodies gravitationally bound to it. This encompasses 8 major planets, 5 officially recognized dwarf planets, hundreds of thousands of asteroids, billions of comets and icy bodies, and an innumerable quantity of interplanetary dust and gas. All these components orbit the Sun, which, despite its average size among stars, constitutes over 99.8% of the solar system's total mass, thereby dictating the gravitational dynamics that govern every object within its sphere of influence. Our solar system is not an isolated entity. It is nestled within the Orion arm of the Milky Way galaxy, a barred spiral galaxy estimated to contain between 100 and 400 billion stars. From a galactic perspective, our solar system is but a tiny speck, located approximately 27,000 light-years from the galactic center, orbiting it once every 225–250 million years. This grand galactic journey, known as a cosmic year, reminds us of the larger scales at play, and the continuous motion inherent in the universe. The Sun and its planetary entourage are not static. They are part of a colossal, rotating system, ever moving through the interstellar medium. Humanity's understanding of the solar system has undergone a profound transformation over millennia, a journey from mythological interpretations to sophisticated scientific models. For much of recorded history, the prevailing view was the geocentric model, championed by ancient Greek philosophers like Aristotle and Ptolemy. This model posited that Earth was the stationary center of the universe, with the Sun, Moon, planets, and stars revolving around it in perfect crystalline spheres. This intuitive model, aligning with direct human observation, the Sun and stars, appear to move across the sky, held sway for nearly 1,400 years, deeply intertwined with philosophical and religious doctrines. However, as astronomical observations became more precise, particularly with the meticulous data collected by Tycho Brahe, inconsistencies began to emerge. The retrograde motion of planets, their apparent backward loop in the sky, was particularly challenging to explain within a strictly geocentric framework, requiring increasingly complex and cumbersome epicycles. The intellectual revolution that dismantled the geocentric paradigm began in the 16th century with Nicolaus Copernicus. His heliocentric model, published posthumously in De Revolutionibus Orbium Coelestium on the revolutions of the heavenly spheres in 1543, boldly proposed that the Sun, not Earth, was the center of the solar system, with Earth and other planets orbiting it. While Copernicus's model still relied on perfect circular orbits, it offered a far simpler and more elegant explanation for planetary motions, including retrograde motion, which was naturally accounted for by Earth's own orbital movement. The Copernican revolution was further advanced by Johannes Kepler, who, using Brahe's precise data, formulated his 3 laws of planetary motion in the early 17th century. Kepler's groundbreaking insight was that planetary orbits are not perfect circles, but ellipses, with the Sun at one focus. This radical departure from ancient dogma provided a mathematically accurate description of planetary paths. Simultaneously, Galileo Galilei's telescopic observations provided crucial empirical evidence supporting the heliocentric view. His discovery of the phases of Venus mirroring those of the Moon, which could only be explained if Venus orbited the Sun and the moons of Jupiter, demonstrating that not all celestial bodies orbited Earth, dealt severe blows to the geocentric model. Finally, Isaac Newton, in his Principia Mathematica 1687, synthesized these observations and laws into a universal theory of gravitation, explaining why planets orbit the Sun, and providing the physical framework for understanding the solar system's mechanics. This scientific revolution marked a fundamental shift in human thought, moving from Earth-centric to cosmos-centric perspectives, and laid the groundwork for modern astronomy. The prevailing scientific explanation for the solar system's genesis is the nebular hypothesis, a theory that has been refined and corroborated by decades of astronomical observation and astrophysical modeling. This hypothesis posits that approximately 4.6 billion years ago, our solar system began as a vast rotating cloud of interstellar gas and dust, known as a solar nebula. This nebula was primarily composed of hydrogen and helium, remnants from the Big Bang, along with heavier elements forged in the hearts of previous generations of stars, and dispersed by supernova explosions. A disturbance, perhaps the shockwave from a nearby supernova, is thought to have triggered the collapse of this nebula. As the cloud collapsed under its own gravity, it began to spin faster due to the conservation of angular momentum, much like a spinning ice skater pulls their arms in to increase their rotation speed. This rapid rotation caused the cloud to flatten into a protoplanetary disk, with a dense, hot core forming at its center. Within this protoplanetary disk, the material began to differentiate. The central core, accumulating most of the mass, became increasingly hot and dense, eventually reaching temperatures and pressures sufficient to initiate nuclear fusion, the process by which hydrogen atoms fuse to form helium, releasing enormous amounts of energy. This marked the birth of our Sun, a main sequence star. Further out in the disk, away from the intense heat of the nascent Sun, the remaining gas and dust began to coalesce through a process called accretion. Microscopic dust grains collided and stuck together, gradually forming larger and larger clumps. This process, sometimes referred to as runaway accretion, led to the formation of planetesimals, bodies ranging from a few kilometers to hundreds of kilometers in size. These planetesimals, in turn, continue to collide and merge, eventually growing into the protoplanets and, finally, the planets we observe today. The differentiation of elements within the disk played a crucial role in determining the composition of the planets. Closer to the hot Sun, only rocky and metallic materials could condense, leading to the formation of the dense terrestrial rocky inner planets: Mercury, Venus, Earth, and Mars. Further out, beyond what is known as the frost line, where temperatures were low enough for volatile compounds like water, methane, and ammonia to condense into ice, the lighter elements and abundant ices could accumulate. This allowed the outer planets Jupiter, Saturn, Uranus, and Neptune to grow into massive gas and ice giants, accumulating vast envelopes of hydrogen and helium gas. The remaining debris that did not coalesce into planets formed the asteroid belt, the Kuiper belt, and the distant Oort cloud, which are reservoirs of smaller bodies like asteroids and comets. This nebular hypothesis is strongly supported by observations of other star systems, where protoplanetary disks have been directly imaged, providing compelling evidence for this formation mechanism. The solar system is a highly structured and diverse collection of celestial bodies. At its heart is the Sun, a G-type main sequence star, the source of all light and heat that sustains life on Earth. Orbiting the Sun are 8 officially recognized planets, broadly categorized into 2 groups based on their composition and location. The inner solar system is home to the 4 terrestrial planets: Mercury, Venus, Earth, and Mars. These planets are relatively small, dense, and composed primarily of rock and metal, with solid surfaces. They are characterized by their proximity to the Sun, and their relatively thinner non-existent atmospheres, except for Venus, which has a very dense atmosphere. Beyond Mars lies the asteroid belt, a region populated by millions of rocky bodies, ranging in size from dust particles to hundreds of kilometers across, with Ceres being the largest and classified as a dwarf planet. Further out, in the cold, outer reaches of the solar system, reside the 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. Jupiter and Saturn are classified as gas giants, predominantly composed of hydrogen and helium, with no solid surface, but rather a gradual transition from gaseous atmosphere to liquid metallic hydrogen interiors. They are characterized by their immense size, rapid rotation, and extensive systems of rings and moons. Uranus and Neptune are often referred to as ice giants, as their interiors contain a significant proportion of heavier volatile compounds like water, methane, and ammonia, in addition to hydrogen and helium. They also possess ring systems and numerous moons. Beyond Neptune lies the Kuiper belt, a vast disc-shaped region similar to the asteroid belt, but much larger and populated by icy bodies, including several dwarf planets such as Pluto, Haumea, and Makemake. This region is thought to be the source of short-period comets. Even further out, extending perhaps a light year or more from the Sun, is the hypothetical Oort cloud, a spherical shell of icy planetesimals, believed to be the source of long-period comets. Interspersed throughout the solar system are countless comets, icy bodies that develop spectacular tails of gas and dust when they approach the Sun, and various forms of interplanetary dust and plasma. Each of these components plays a unique role in the intricate dynamics and evolution of our cosmic home. The sheer scale of the solar system is difficult to grasp, often requiring specialized units of measurement. Within the solar system, the primary unit of distance is the astronomical unit, defined as the average distance from the Earth to the Sun, approximately 149.6 million kilometers, 93 million miles. This unit is convenient for expressing distances within our planetary system. For instance, Jupiter is about 5.2 astronomical unit from the Sun, while Neptune is about 30 astronomical unit away. However, when discussing distances beyond the solar system, even the astronomical unit becomes too small. For interstellar distances, astronomers use the light year, which is the distance light travels in one Earth year in a vacuum, approximately 9.46 trillion kilometers, 5.88 trillion miles. To put this into perspective, the nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. The Milky Way galaxy itself spans about 100,000 light-years in diameter. These vast distances highlight the emptiness of space and the immense cosmic canvas upon which our solar system is painted. Understanding these scales is crucial for appreciating the challenges and triumphs of space exploration, and for contextualizing our place in the universe. The time scales are equally immense. The solar system has existed for 4.6 billion years, a period almost incomprehensibly long to the human mind, during which geological and evolutionary processes have unfolded. The study of the solar system is far from a purely academic exercise. It holds profound relevance for humanity on multiple fronts. Firstly, it offers a unique laboratory for understanding planetary formation and evolution. By studying the diverse range of planets, moons, and smaller bodies, scientists can test and refine theories about how planetary systems form and change over cosmic timescales. This knowledge is increasingly vital as we discover thousands of exoplanets orbiting other stars, allowing us to compare our solar system with others, and gain insights into the prevalence of different types of planetary architectures. Secondly, the solar system is our immediate cosmic backyard, and understanding its environment is crucial for future human endeavors. As we contemplate sending humans to Mars, establishing lunar bases, or even venturing further into the outer solar system, detailed knowledge of radiation environments, resource availability, and potential hazards becomes paramount. The study of asteroids and comets, for instance, is not only about understanding their origins, but also about assessing potential impact risks to Earth, and identifying potential sources of valuable resources. Thirdly, the search for life beyond Earth is intrinsically linked to our understanding of the solar system. Missions to Mars, Europa, Enceladus, and Titan are specifically designed to look for signs of past or present habitability, focusing on the presence of liquid water, energy sources, and organic molecules. These investigations not only address the profound question of whether we are alone in the universe, but also deepen our understanding of the conditions necessary for life to emerge and thrive. Fourthly, studying the Sun and its activity space weather is critical for protecting our technological infrastructure on Earth, including satellites, power grids, and communication systems, which can be severely impacted by solar flares and coronal mass ejections. Finally, the exploration of the solar system inspires generations, pushing the boundaries of human ingenuity and technological advancement. It fosters scientific literacy, encourages critical thinking, and reminds us of the shared human endeavor to explore the unknown. The mysteries that still shroud many aspects of our solar system continue to drive scientific inquiry, promising new discoveries, and a deeper appreciation for the cosmic ballet that unfolds around us. This introductory overview sets the stage for a more detailed exploration of each of the solar system's fascinating components, and the celestial patterns that guide our gaze to the stars. The journey through the planets and constellations promises to be one of enlightenment and wonder, revealing the intricate beauty and profound scientific narratives woven into the fabric of our cosmic home. The Sun, our star and its influence. Having established the foundational context of our solar system, we now turn our attention to its undisputed monarch, the celestial body that dominates its mass, dictates its dynamics, and provides the very energy that makes life on Earth possible. The Sun. Far from being a simple ball of fire, the Sun is a complex, dynamic star, a G-type main sequence star, currently in the most stable phase of its life cycle. Its immense gravitational pull governs the orbits of all planets, dwarf planets, asteroids, and comets, ensuring the cosmic ballet continues with precision. More profoundly, the Sun is a colossal nuclear furnace, converting mass into energy through nuclear fusion, a process that has powered it for billions of years, and will continue to do so for billions more. Understanding the Sun's intricate structure, the phenomena that occur on and within it, its profound influence on Earth and the wider solar system, and its ultimate fate, is paramount to comprehending the very essence of our cosmic home. The Sun, like all stars, is a massive sphere of plasma, primarily composed of hydrogen about 73% by mass, and helium about 25% by mass, with trace amounts of heavier elements. Its internal structure is layered, much like an onion, each layer playing a distinct role in the generation and transport of energy. At the very heart of the Sun lies the core, extending from the center to about 20–25% of the solar radius. This is the engine room of the Sun, where temperatures reach an astounding 15 million degrees Celsius, 27 million degrees Fahrenheit, and pressures are 250 billion times that of Earth's atmospheric pressure at sea level. Under these extreme conditions, hydrogen nuclei protons are forced together in a series of nuclear fusion reactions, known as the proton-proton chain. In this process, 4 hydrogen nuclei combine to form one helium nucleus, releasing a tremendous amount of energy in the form of gamma-ray photons and neutrinos. It is this continuous fusion that powers the Sun, providing the outward pressure that counteracts the inward pull of gravity, maintaining the star's hydrostatic equilibrium. Without this constant energy generation, the Sun would collapse under its own immense weight. Surrounding the core is the radiative zone, extending from about 25% to 70% of the solar radius. In this zone, energy generated in the core is transported outwards primarily by radiation. Photons, particularly gamma-ray and X-ray photons, are repeatedly absorbed and re-emitted by the dense plasma. This is an incredibly slow process. A single photon can take tens of thousands, or even hundreds of thousands, of years to zigzag its way through the radiative zone, undergoing countless collisions and deflections before reaching the next layer. The plasma in this region is so dense that photons travel only a few millimeters before being absorbed and re-emitted in a random direction. This tortuous journey is a testament to the extreme conditions within the Sun. Beyond the radiative zone lies the convective zone, which extends from about 70% of the solar radius to the visible surface. Here, the plasma is cooler and less dense, allowing for energy transport primarily through convection. Hot plasma rises towards the surface, carrying energy with it, cools, and then sinks back down, creating vast circulating currents, much like boiling water in a pot. These convective cells are responsible for the granular appearance of the Sun's surface, with brighter, hotter regions granules where plasma is rising and darker, cooler regions where it is sinking. This turbulent motion is crucial for bringing the energy generated in the core to the surface. The visible surface of the Sun is called the photosphere, a relatively thin layer only a few hundred kilometers thick, from which most of the sunlight we see is emitted. The temperature here is about 5,500 degrees Celsius, 9,940 degrees Fahrenheit. Despite its appearance as a solid surface, the photosphere is still gaseous, but it is dense enough to become opaque to light, marking the point where photons can finally escape into space. It is in the photosphere that we observe features like sunspots, which are darker, cooler regions around 3,500 degrees Celsius, caused by intense magnetic activity suppressing convection. These sunspots often appear in groups and are a key indicator of solar activity. Above the photosphere lies the Sun's atmosphere, which consists of 2 main layers: the chromosphere and the corona. The chromosphere, meaning color sphere, is a reddish layer visible during total solar eclipses when the brighter photosphere is blocked. It is hotter than the photosphere, with temperatures increasing with altitude, ranging from about 6,000 to 20,000 degrees Celsius. This layer is characterized by spicules, which are dynamic, jet-like structures of gas that extend outwards. The outermost layer of the Sun's atmosphere is the corona, a superheated tenuous plasma that extends millions of kilometers into space. The corona is incredibly hot, reaching temperatures of over 1 million degrees Celsius, 1.8 million degrees Fahrenheit, a phenomenon that remains a subject of active research, though it is believed to be heated by complex magnetic processes. The corona is also the source of the solar wind, a continuous stream of charged particles flowing outwards from the Sun. The Sun's energy generation through nuclear fusion is a process of immense efficiency and power. Every second, the Sun converts approximately 600 million tons of hydrogen into 596 million tons of helium. This energy is released primarily as gamma rays, which then undergo the long journey through the radiative and convective zones, before emerging as visible light, ultraviolet radiation, and infrared radiation from the photosphere. This continuous outpouring of energy has sustained the Sun for roughly 4.6 billion years, and it is estimated to have enough hydrogen fuel to continue fusing for another 5 billion years. This stable, long-term energy source is a critical factor in the development and sustenance of life on Earth, providing a consistent energy input for photosynthesis, and maintaining a habitable temperature range. The Sun is not a static, unchanging sphere. It is a highly active and dynamic star, exhibiting a range of phenomena collectively known as solar activity. These phenomena are driven by the Sun's complex and powerful magnetic field, which is generated by the movement of electrically charged plasma in the convective zone. Sunspots, as mentioned, are the most visible manifestation of solar activity. They are regions where strong magnetic fields emerge from the Sun's interior, inhibiting the convection of hot plasma, and making these areas cooler and thus darker. Sunspots follow an approximately 11-year cycle, known as the solar cycle or sunspot cycle, during which the number of sunspots waxes and wanes, reaching a maximum and then a minimum. This cycle is associated with the reversal of the Sun's global magnetic field. Solar flares are sudden, intense bursts of radiation emanating from the Sun's surface, often associated with sunspot regions. They are caused by the sudden release of magnetic energy that is built up in the solar atmosphere. Flares release enormous amounts of energy across the electromagnetic spectrum, from radio waves to X-rays and gamma rays, and can last from minutes to hours. Coronal mass ejection (CMEs) are even more dramatic events, involving the expulsion of vast clouds of magnetized plasma from the Sun's corona into space. CMEs are often associated with solar flares, but can also occur independently. They can carry billions of tons of material at speeds of hundreds to thousands of kilometers per second. If a CME is directed towards Earth, it can have significant impacts. The solar wind is a continuous stream of charged particles, protons, electrons, alpha particles that flows outwards from the Sun's corona, at speeds of hundreds of kilometers per second. It is essentially the expansion of the superheated corona into interplanetary space. While less dramatic than flares or CMEs, the solar wind constantly interacts with the magnetic fields and atmospheres of planets throughout the solar system. The Sun's activity has a profound and direct impact on Earth, influencing our planet's magnetic field, atmosphere, and even technological infrastructure. When solar flares or CMEs are directed towards Earth, they can trigger geomagnetic storms. These storms occur when the charged particles and magnetic fields from the Sun interact with Earth's magnetosphere, the protective magnetic bubble surrounding our planet. The interaction can cause temporary disturbances in Earth's magnetic field, leading to several observable effects. One of the most visually stunning impacts is the creation of auroras, the spectacular light displays seen in the polar regions of Aurora Borealis in the north, Aurora Australis in the south. When charged particles from the solar wind or CMEs penetrate Earth's upper atmosphere, they collide with atoms and molecules of gases like oxygen and nitrogen, exciting them. As these excited atoms return to their normal energy state, they emit light of various colors, creating the shimmering curtains of the aurora. Beyond the aesthetic, solar activity poses significant challenges to modern technology. Geomagnetic storms can induce strong electrical currents in long conductors, such as power transmission lines, potentially leading to widespread power outages by overloading transformers. They can also disrupt radio communications, particularly high-frequency radio, which relies on the ionosphere, a layer of Earth's atmosphere that is affected by solar radiation. Satellite operations are also vulnerable. Charged particles can damage electronic components, cause single-event upsets, temporary malfunctions, or even lead to permanent satellite failures. GPS signals can be degraded, and astronauts in orbit face increased radiation exposure during intense solar events. Understanding and predicting space weather is therefore a critical area of research, with agencies like NOAA's Space Weather Prediction Center constantly monitoring the Sun to provide warnings. While the Sun's long-term activity has been linked to minor climate variations on Earth, e.g. the Maunder Minimum, a period of low sunspot activity that coincided with the Little Ice Age, its direct impact on contemporary global warming is considered negligible compared to anthropogenic greenhouse gas emissions. The Sun, like all stars, has a finite lifespan, though it is incredibly long by human standards. Our Sun is currently in the most stable phase of its life, known as the main sequence. It has been on the main sequence for approximately 4.6 billion years and is expected to remain there for another 5 billion years. During this phase, it fuses hydrogen into helium in its core, maintaining a stable size and luminosity. However, as the hydrogen fuel in the core begins to deplete, the Sun will undergo significant evolutionary changes. In about 5 billion years, when most of the hydrogen in its core has been converted to helium, the core will begin to contract under gravity, causing it to heat up. This increased temperature will ignite a shell of hydrogen fusion around the helium core. The energy released from this shell fusion will cause the Sun's outer layers to expand dramatically, and its surface temperature will cool, turning it into a red giant. During this phase, the Sun's radius will swell to such an extent that it will engulf Mercury, Venus, and possibly even Earth. The oceans on Earth would boil away long before the Sun's expansion reaches our planet's orbit, rendering it uninhabitable. After the red giant phase, the Sun's core will become hot and dense enough to begin fusing helium into carbon and oxygen, in a process called the triple alpha process. This phase is relatively brief. Once the helium fuel in the core is exhausted, the Sun will shed its outer layers, forming a beautiful, expanding shell of gas known as a planetary nebula. This nebula will disperse into interstellar space, enriching the galaxy with heavier elements. What remains of the Sun will be its incredibly dense, hot core, a stellar remnant known as a white dwarf. A white dwarf is roughly the size of Earth, but contains about half the mass of the original Sun, packed into an incredibly small volume. It will no longer undergo nuclear fusion, but will slowly cool down over billions of years, radiating its residual heat into space, eventually becoming a cold dark black dwarf, though the universe is not old enough for any black dwarfs to have formed yet. This solar life cycle, from birth in a nebula to eventual demise as a white dwarf, is a common fate for stars of the Sun's mass, a testament to the grand cosmic recycling of matter and energy that shapes the universe. The Sun's gravitational dominance is the fundamental force that structures our solar system. Its immense mass creates a gravitational well so profound that it dictates the orbits of all other celestial bodies, from the closest planet Mercury to the most distant comets in the Oort cloud. The laws of celestial mechanics, particularly Kepler's laws of planetary motion and Newton's law of universal gravitation, precisely describe how these bodies move under the Sun's influence. Planets orbit the Sun in elliptical paths, with their orbital speed varying depending on their distance from the Sun, faster when closer, slower when farther. The Sun's gravity also plays a crucial role in tidal forces, though its effect on Earth's tides is less pronounced than that of the Moon. Beyond its gravitational pull, the Sun's radiation pressure and solar wind also exert subtle but continuous forces on smaller bodies, particularly comets, shaping their tails as they approach the inner solar system. The Sun is not merely a source of light and heat. It is the gravitational anchor, the energy provider, and the dynamic orchestrator of the entire solar system, the constant reminder of the fundamental forces that govern the cosmos and enable the existence of life as we know it. Its study continues to reveal new complexities and insights into stellar physics, space weather, and the intricate dance of celestial bodies that define our home in the universe. Inner planets. Terrestrial worlds. Mercury, Venus. Having explored the majestic Sun, the gravitational and energetic heart of our solar system, we now embark on a journey inward, to the fiery crucible of the inner solar system, home to the terrestrial planets. These four worlds, Mercury, Venus, Earth, and Mars, share fundamental characteristics. They are relatively small, dense, and composed primarily of rock and metal, possessing solid surfaces. Their formation close to the Sun meant that only materials with high condensation temperatures could coalesce, leading to their rocky nature. In this third part of our lecture, we will delve into the two innermost terrestrial planets. Mercury, the swift messenger, and Venus, the veiled and scorching world. Both offer stark contrasts to Earth, providing invaluable insights into planetary evolution under extreme conditions, and the diverse paths that rocky worlds can take. Mercury, the swift, scorched messenger. Mercury, the smallest and innermost planet in our solar system, is a world of extremes, a heavily cratered sphere that races around the Sun with astonishing speed. Its name, derived from the Roman messenger god, perfectly encapsulates its rapid orbital period. Orbiting at an average distance of just 0.39 astronomical unit from the Sun, Mercury completes a full revolution in a mere 88 Earth days, making its year shorter than any other planets. However, its rotation period is surprisingly slow. For a long time, it was believed that Mercury was tidally locked to the Sun, always showing the same face, much like the Moon is tidally locked to Earth. This misconception was based on early radar observations that were misinterpreted. Later, more precise radar measurements in the 1960s revealed a fascinating 3-2 spin orbit resonance. Mercury completes 3 rotations on its axis for every 2 orbits it makes around the Sun. This means that a solar day on Mercury, the time from one sunrise to the next, is incredibly long, lasting about 176 Earth days, or 2 Mercurian years. This unique resonance is a consequence of the strong tidal forces exerted by the nearby Sun. The proximity to the Sun dictates Mercury's most striking characteristic: its extreme temperature variations. During its long day, temperatures on the sunlit side can soar to a blistering 430 degrees Celsius (800 degrees Fahrenheit), hot enough to melt lead. Conversely, during its equally long night, temperatures plummet to a frigid 180 degrees Celsius (290 degrees Fahrenheit). This is the largest temperature swing of any planet in the solar system, a testament to its lack of a substantial atmosphere to trap and distribute heat. Mercury possesses only an extremely thin exosphere, a tenuous layer of atoms, primarily hydrogen, helium, oxygen, sodium, potassium, and calcium, that are constantly being blasted off its surface by the solar wind in macrometeorite impacts, only to be replenished from the planet's surface or captured from the solar wind. This atmosphere is far too thin to retain heat or protect the surface from impacts. Mercury's surface bears a striking resemblance to Earth's moon. It is heavily cratered, a result of billions of years of bombardment by asteroids and comets since its formation. These craters range in size from tiny bowl-shaped depressions to enormous multi-ring basins. The most prominent feature is the Caloris Basin, one of the largest impact basins in the solar system, spanning approximately 1,550 kilometers (960 miles) in diameter. The impact that created Caloris was so powerful that it sent seismic waves reverberating through the planet, creating a chaotic hilly terrain on the exact opposite side of the planet, aptly named the Weird Terrain. Beyond craters, Mercury's surface also features vast smooth plains, likely formed by ancient volcanic flows that filled in older impact basins, similar to the lunar Morea. Another distinctive feature is the presence of numerous scarps or lobate cliffs, some hundreds of kilometers long and several kilometers high. These scarps are believed to be evidence of Mercury's crust contracting as its interior cooled and shrank over billions of years, causing the surface to buckle and fold. Despite its small size, Mercury is remarkably dense, suggesting a large metallic core. Planetary scientists believe it has an unusually large iron core, comprising about 85% of its radius, which is proportionally larger than any other planet in the solar system. This large core is thought to be partially molten, and surprisingly, Mercury possesses a weak but global magnetic field. This discovery by the Mariner 10 spacecraft in the 1970s was unexpected for such a small, slowly rotating planet, as a strong magnetic field is typically associated with a rapidly rotating, convecting liquid outer core, the dynamo effect. The exact mechanism for Mercury's magnetic field is still a subject of ongoing research, but it suggests that its core is indeed still partially liquid and undergoing some form of convection. Missions like NASA's Messenger Mercury Surface, Space Environment, Geochemistry, and Ranging spacecraft, which orbited Mercury from 2011 to 2015, provided unprecedented data, revealing the planet's surface composition, the presence of water ice and permanently shadowed craters at its poles, where temperatures are perpetually low enough for ice to survive, despite the planet's overall heat, and further insights into its magnetic field and internal structure. The joint European-Japanese BP Colombo mission, currently en route to Mercury, promises to provide even more detailed observations upon its arrival. Venus. The veiled volcanic inferno. Venus, named after the Roman goddess of love and beauty, is often referred to as Earth's sister planet, due to its similar size, mass, and bulk composition. However, this superficial resemblance belies a profoundly different and hostile reality. Venus is a world of extreme heat, crushing atmospheric pressure, and perpetual cloud cover, a stark warning of a runaway greenhouse effect. Orbiting at an average distance of 0.72 astronomical unit from the Sun, Venus completes an orbit in 225 Earth days. What makes Venus truly unique among the major planets is its retrograde rotation. It rotates on its axis in the opposite direction to most other planets, and incredibly slowly. A single rotation takes 243 Earth days, meaning a Venusian day is longer than its year. This results in the Sun rising in the west and setting in the east, though the thick clouds obscure any direct view of the Sun from the surface. The reason for this retrograde and slow rotation is not fully understood, but is thought to be a result of a massive impact early in its history or complex tidal interactions with the Sun. The most defining characteristic of Venus is its dense and toxic atmosphere. It is composed almost entirely of carbon dioxide (CO2), with trace amounts of nitrogen and other gases. This atmosphere is incredibly thick, exerting a surface pressure over 90 times that of Earth's sea level pressure, equivalent to the pressure experienced at a depth of nearly a kilometer, half a mile in Earth's oceans. The thick CO2 atmosphere is a potent greenhouse gas, trapping solar radiation and leading to a runaway greenhouse effect. This process has elevated Venus's surface temperature to an astonishing average of 462 degrees Celsius (864 degrees Fahrenheit), making it the hottest planet in the solar system, hotter even than Mercury, despite being farther from the Sun. This temperature is hot enough to melt lead and zinc, and it is remarkably uniform across the entire planet, day or night, due to the efficient circulation of the dense atmosphere. Adding to the extreme conditions, Venus's atmosphere is perpetually shrouded by thick opaque clouds, composed primarily of sulfuric acid droplets. These clouds reflect about 70% of the incoming sunlight, which is why Venus appears so bright in our sky, earning it the moniker morning star or evening star. However, these clouds also contribute to the greenhouse effect and create a highly corrosive environment. Lightning storms are also common within these clouds. The constant presence of these clouds has historically made direct observation of Venus's surface impossible from Earth, necessitating radar mapping and lander missions. Radar mapping, primarily by NASA's Magellan spacecraft in the early 1990s, revealed Venus's surface to be dominated by volcanic features. Vast plains formed by extensive lava flows cover about 80% of the planet. There are also numerous volcanoes, ranging from small domes to massive shield volcanoes, though none appear to be currently active on a large scale. However, evidence suggests that Venus has undergone significant volcanic resurfacing events in its geological past, perhaps wiping clean much of its older crater terrain. Some scientists hypothesize that Venus experiences periodic global resurfacing events due to the buildup of internal heat, leading to widespread volcanic activity. Other prominent surface features include tesserae, highly deformed and fractured regions that are thought to be older crustal material, and coronae, large, ring-like structures believed to be caused by upwellings of magma from the planet's interior. Unlike Earth, Venus shows no evidence of plate tectonics, the process that continuously reshapes Earth's surface. Venus also lacks a significant global magnetic field. This absence is puzzling given its similar size and presumed iron core to Earth. The most widely accepted explanation is its incredibly slow rotation. A planetary dynamo, which generates a magnetic field, requires not only a liquid electrically conductive core, but also sufficient rotation to drive convection currents within that core. Venus's sluggish rotation is likely insufficient to sustain a dynamo, leaving it exposed to the full force of the solar wind, which has probably stripped away any water that might have once existed on its surface over billions of years. Evidence from past missions suggests that Venus may have once had oceans of liquid water, but the runaway greenhouse effect boiled them away, with the water vapor then escaping into space. The exploration of Venus has been a challenging but rewarding endeavor. Early missions, particularly the Soviet Venera series in the 1970s and early 1980s, were the first to successfully land on Venus's surface, providing brief but invaluable glimpses of the hellish landscape and direct measurements of the atmospheric conditions. These landers survived for only a short time, less than 2 hours, before succumbing to the extreme heat and pressure. NASA's Magellan mission, using radar, created the most comprehensive map of Venus's surface, revealing its volcanic terrain. More recently, the European Space Agency's Venus Express Orbiter 2006-2014 studied Venus's atmosphere and plasma environment, confirming the ongoing loss of water from its upper atmosphere. Future missions, such as NASA's Da Vinci Plus Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, and Vereda's Venus Emissivity, Radio Science, INSER, Topography, and Spectroscopy missions, are planned to further investigate Venus's atmospheric evolution, geological history, and potential for past habitability, seeking to understand why Earth's sister planet took such a dramatically different evolutionary path. In summary, Mercury and Venus, while both terrestrial planets, represent two distinct extremes in planetary evolution. Mercury, a small, airless, and heavily cratered world, showcases the direct and brutal impact of solar proximity and the challenges of retaining volatile compounds. Venus, on the other hand, stands as a stark testament to the destructive power of a runaway greenhouse effect, transforming a potentially Earth-like world into a scorching, high-pressure inferno. Their study provides crucial data for comparative planetology, helping us to understand the complex interplay of internal processes, solar radiation, and atmospheric dynamics that shape rocky worlds, and offering vital context for our unique and life-sustaining Earth. Inner planets. Terrestrial worlds Earth, Mars. Having ventured through the scorching extremes of Mercury and the veiled inferno of Venus, our journey through the inner solar system now brings us to the two terrestrial planets most intimately familiar to humanity. Earth, our vibrant home, and Mars, the enigmatic red planet, a world of enduring fascination and future aspirations. While sharing the fundamental characteristics of rocky composition and solid surfaces with their inner siblings, Earth and Mars present a compelling study in contrasts, offering profound insights into the conditions necessary for life and the delicate balance of planetary evolution. This fourth part of our lecture will delve into the unique attributes that make Earth a cradle for life, and then explore Mars, its geological history, its potential for past habitability, and the relentless human quest to understand its secrets. Earth, the blue marble, the cradle of life. Earth, the third planet from the Sun, stands as a singular anomaly in our solar system, a vibrant blue marble teeming with life. Its uniqueness stems from a confluence of precisely tuned conditions that have allowed liquid water to persist on its surface for billions of years, fostering the evolution of an astonishing diversity of life forms. Orbiting at an average distance of 1 astronomical unit 149.6 million kilometers from the Sun, Earth experiences a temperate climate, a crucial factor in maintaining water in its liquid state. Its axial tilt of approximately 23.5 degrees is responsible for the seasons, distributing solar energy across the planet throughout the year. Earth completes one orbit around the Sun in roughly 365.25 days, defining our year, and rotates on its axis approximately every 24 hours, giving us our day-night cycle. The most defining characteristic of Earth is the abundant presence of liquid water on its surface. Covering over 70% of the planet, Earth's oceans, lakes, and rivers are fundamental to its climate, geology, and biology. Water's high specific heat capacity helps moderate global temperatures, and its ability to dissolve a wide range of substances makes it an ideal solvent for biochemical reactions. The water cycle, driven by solar energy, continuously circulates water through evaporation, condensation, precipitation, and runoff, shaping landscapes and sustaining ecosystems. The presence of a substantial atmosphere is equally critical. Earth's atmosphere is primarily composed of nitrogen 78% and oxygen 21%, with trace amounts of argon, carbon dioxide, and other gases. The oxygen, a byproduct of photosynthesis by early life forms, is vital for complex life as we know it. The atmosphere provides a breathable environment, distributes heat around the globe, and protects the surface from harmful solar radiation and meteoroid impacts. Crucially, the ozone layer within the stratosphere absorbs most of the sun's dangerous ultraviolet UV radiation, preventing it from reaching the surface and causing widespread damage to living organisms. Earth's dynamic interior also plays a pivotal role in its habitability. The planet has a differentiated structure, with a solid inner core of iron and nickel, a liquid outer core, a thick mantle, and a thin crust. The convection currents within the liquid outer core generate Earth's powerful global magnetic field, known as the magnetosphere. This magnetic field acts as a protective shield, deflecting the vast majority of harmful charged particles from the solar wind and cosmic rays, preventing them from stripping away our atmosphere and irradiating the surface. Without this magnetic field, Earth's atmosphere would likely have been eroded over geological timescales, much like Mars, and the surface would be exposed to lethal radiation. Another unique geological process on Earth is plate tectonics. The Earth's lithosphere crust and uppermost mantle is broken into several large plates that are constantly moving, driven by convection currents in the mantle. This process leads to phenomena like continental drift, mountain building, earthquakes, and volcanism. Plate tectonics is crucial for the long-term regulation of Earth's climate through the carbon silicate cycle. Volcanic activity releases carbon dioxide into the atmosphere, while the weathering of silicate rocks on land absorbs CO2, eventually transporting it to the oceans where it forms carbonates. This cycle acts as a thermostat, helping to stabilize Earth's temperature over millions of years, preventing it from becoming either a frozen wasteland or Venus-like inferno. The continuous recycling of crustal material also brings fresh nutrients to the surface, supporting biological activity. Earth's large natural satellite, the Moon, also exerts a significant influence. Its gravitational pull is the primary driver of Earth's ocean tides, which play a role in coastal ecosystems. More importantly, the Moon's relatively large size and close proximity stabilize Earth's axial tilt, preventing dramatic and chaotic wobbles that could lead to extreme climate swings over geological time. This orbital stability has provided a consistent environment conducive to the long-term evolution of complex life. The intricate interplay of these factors, liquid water, a protective atmosphere, a strong magnetic field, active plate tectonics, and a stabilizing moon, creates a remarkably stable and dynamic environment that has allowed life to flourish and evolve into the incredible diversity we see today. Earth serves as the ultimate benchmark in the search for life elsewhere in the universe, providing a living example of a habitable world. Mars, the red planet, a world of past and future. Mars, the fourth planet from the Sun, is often called the Red Planet due to the pervasive iron oxide's rust on its surface. It has captivated humanity for centuries, inspiring countless stories of alien civilizations and serving as the primary target for future human exploration. Orbiting at an average distance of 1.52 astronomical unit from the Sun, Mars has a year lasting 687 Earth days and a day length very similar to Earth's, at about 24.6 hours. Its axial tilt 25.2 degrees is also comparable to Earth's, resulting in distinct seasons, though they are longer and more extreme, due to its more eccentric orbit and thinner atmosphere. Mars' surface is a dramatic landscape of craters, vast plains, enormous volcanoes, and deep canyons. Like Mercury, it bears the scars of ancient impacts, though erosion by wind and possibly water has softened many of them. The most striking geological features include Olympus Mons, the largest volcano in the solar system, a colossal shield volcano that stands over 21 kilometers 13 miles high, and spans 600 kilometers 370 miles at its base, roughly the size of Arizona. Its immense size is attributed to the lack of plate tectonics on Mars, allowing magma plumes to erupt repeatedly at the same location over billions of years. Another prominent feature is Valles Marineris, an enormous canyon system stretching over 4,000 kilometers 2,500 miles long, up to 200 kilometers 120 miles wide, and 7 kilometers 4.3 miles deep. This vast chasm dwarfs Earth's Grand Canyon, and is believed to have formed through tectonic fracturing and erosion. Perhaps the most compelling aspect of Mars is the abundant evidence of past liquid water on its surface. Orbital missions and rovers have revealed numerous geological features that strongly suggest the presence of ancient rivers, lakes, and even oceans. These include dried-up riverbeds, deltas, sedimentary rock layers, and minerals that form only in the presence of water, e.g., hematite blueberries, found by the Opportunity rover, and clays. While liquid water cannot persist on the surface today due to Mars' low atmospheric pressure and cold temperatures, it would either freeze or boil away. The evidence points to a warmer, wetter past, perhaps billions of years ago. Today, water on Mars exists primarily as ice in its polar ice caps, which also contain frozen carbon dioxide, and likely beneath the surface in vast reservoirs of permafrost. Subsurface ice has been directly detected by missions like Phoenix Lander and Mars Reconnaissance Orbiter. The presence of water, even if mostly frozen, is crucial for future human missions and the potential for extant microbial life. Mars has a very thin atmosphere, about 1% the density of Earth's, composed primarily of carbon dioxide 95%, with small amounts of nitrogen, argon, and other gases. This thin atmosphere provides little protection from solar radiation or macrometeoroids, and results in extreme temperature swings between day and night, from around 20 degrees Celsius 68 degrees Fahrenheit at the equator during summer day, to 140 degrees Celsius 220 degrees Fahrenheit at the poles in winter. The thin atmosphere is also responsible for frequent and sometimes planet-encircling dust storms, which can obscure the surface for weeks or months, posing challenges for robotic missions. Unlike Earth, Mars has lost most of its primordial atmosphere over billions of years. This atmospheric loss is attributed to a combination of factors. Mars' weaker gravity compared to Earth, its lack of a strong global magnetic field which would protect it from the solar wind, and impacts from asteroids and comets. Evidence from NASA's MAVEN Mars Atmosphere and Volatile Evolution mission suggests that the solar wind has played a significant role in stripping away Mars' atmosphere over time. Mars has two small, irregularly shaped moons, Phobos and Deimos, which are widely believed to be captured asteroids, rather than formed in situ. They are much smaller than Earth's moon and orbit very close to Mars. Phobos, the inner moon, is slowly spiraling inwards, and is predicted to either crash into Mars or break up into a ring within tens of millions of years. The exploration of Mars has been a cornerstone of space science for decades, driven by the enduring question of whether life ever arose there, or if it could support life in the future. Numerous missions from various space agencies have provided an unprecedented wealth of data. NASA's Viking landers in the 1970s were the first to attempt direct searches for microbial life with inconclusive results. Subsequent missions, including the Mars Global Surveyor, Mars Odyssey, Mars Express ESA, and the highly successful Mars exploration rovers Spirit and Opportunity, Phoenix Lander, Curiosity rover, and Perseverance rover with its Ingenuity helicopter, have meticulously studied Mars geology, climate, and potential for habitability. The Perseverance rover, which landed in 2021, is currently collecting rock and soil samples for a future sample return mission to Earth, aiming to find definitive evidence of ancient microbial life. The ongoing search for subsurface water ice and potential subsurface liquid water, e.g., brines, is also a key focus, as these could be crucial resources for future human missions and potential refuge for life. The prospect of human exploration and colonization of Mars is a long-term goal for many space agencies and private companies. Mars offers a relatively accessible target compared to other planets, and its resources, water ice, atmospheric CO2 for fuel and oxygen, could potentially be utilized to sustain a human presence. However, significant challenges remain, including the long journey, radiation exposure, the harsh Martian environment, and the psychological and physiological effects of long-duration spaceflight. Despite these hurdles, Mars continues to beckon as humanity's next great frontier, a testament to our innate drive to explore and expand our presence beyond Earth. The comparative study of Earth and Mars provides a unique natural experiment in planetary evolution. One world that retained its water and atmosphere, fostering life, and another that lost them, becoming a cold, dry desert, yet still holding clues to its ancient, possibly life-bearing past. The asteroid belt and dwarf planet Ceres, Pluto. Our journey through the solar system now takes us beyond the terrestrial planets, into a vast and dynamic region that serves as a boundary between the inner, rocky worlds, and the outer, gaseous giants. The asteroid belt. This region, far from being an empty void, is a bustling thoroughfare of countless rocky and metallic bodies, remnants from the early solar system's formation. Beyond this belt, and extending into the frigid outer reaches, we encounter a fascinating category of celestial objects that defy simple planetary classification: the dwarf planets. This fifth part of our lecture will delve into the characteristics and significance of the asteroid belt, explore the definition and nature of dwarf planets, and then focus on two prominent examples: Ceres, the largest object in the main asteroid belt, and Pluto, the iconic former planet that now reigns as a king of the Kuiper belt. We will also briefly touch upon other notable dwarf planets, and the broader context of the Kuiper belt. The asteroid belt. A failed planet or cosmic debris. The asteroid belt is a torus-shaped region located roughly between the orbits of Mars, at approximately 1.5 astronomical unit, and Jupiter at approximately 5.2 astronomical unit, extending from about 2.2 to 3.2 astronomical unit from the Sun. It is home to millions of small, irregularly shaped bodies known as asteroids or minor planets, ranging in size from mere dust particles to objects hundreds of kilometers in diameter. If all the material in the asteroid belt were combined, its total mass would be less than that of Earth's moon, and significantly less than that of Pluto. This fact immediately dismisses the popular misconception of the asteroid belt as a densely packed field of rocks, akin to an obstacle course for spacecraft. In reality, the average distance between significant asteroids is so vast that spacecraft can easily traverse the belt without incident. The composition of asteroids varies, generally reflecting their distance from the Sun during the solar system's formation. The innermost asteroids tend to be richer in silicates and metals, while those further out contain more carbonaceous material, and even some water ice. Asteroids are broadly classified into three main types. C-type carbonaceous. The most common type, making up over 75% of known asteroids. They are dark in color, rich in carbon, and found predominantly in the outer parts of the belt. They are thought to be primitive, largely unaltered remnants from the early solar system. S-type silicaceous. The second most common, comprising about 17% of known asteroids. They are brighter, stony, and composed primarily of silicates and some metals. They are more common in the inner part of the belt. M-type metallic. Less common, these asteroids are bright and composed mainly of nickel iron. They are believed to be the exposed cores of larger differentiated asteroids that were shattered by impacts. The origin of the asteroid belt is a key piece of the solar system's formation puzzle. The prevailing theory is that it represents material from the protoplanetary disk that never coalesced into a full-fledged planet. Early in the solar system's history, numerous planetesimals formed in this region. However, the immense gravitational influence of Jupiter, the largest planet, prevented these planetesimals from accreting into a single, large body. Jupiter's powerful gravity stirred up the orbits of these nascent bodies, causing them to collide at high velocities. Instead of gently merging, these high-speed collisions often resulted in fragmentation, grinding down larger bodies into smaller pieces. This gravitational perturbation by Jupiter created Kirkwood gaps within the belt, regions where asteroids are scarce due to orbital resonances with Jupiter, where the gravitational tugs from Jupiter repeatedly clear out objects. Despite the fragmentation, some larger asteroids did form and survive. The four largest objects in the main belt are Ceres, Vesta, Pallas, and Hygiea, accounting for about half of the belt's total mass. Vesta is particularly interesting as it is differentiated, meaning it has a core, mantle, and crust, suggesting it grew large enough to undergo internal heating and melting, before the disruptive influence of Jupiter prevented further accretion. The study of asteroids, both through telescopic observation and spacecraft missions like NASA's Dawn mission to Vesta and Ceres, and OSIRIS-REx to asteroid Bennu, provides invaluable insights into the conditions and processes that occurred during the very early stages of planetary formation. Asteroids are essentially time capsules, preserving the primordial material from which the planets were built. Furthermore, some asteroids are considered potential sources of valuable resources e.g., metals, water ice for future space exploration and colonization. Dwarf planets. A new category of worlds. The definition of a planet became a subject of intense scientific debate in the early 21st century, particularly with the discovery of Eris, an object larger than Pluto, in the outer solar system. This led the International Astronomical Union (IAU) to establish a formal definition of a planet in 2006, which also introduced a new category: dwarf planets. According to the IAU, a celestial body is classified as a planet if it meets three criteria. It orbits the Sun. It has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium nearly round shape. It has cleared the neighborhood around its orbit. A dwarf planet meets the first two criteria but fails the third. This means it orbits the Sun and is massive enough to be nearly spherical, but it has not gravitationally cleared its orbital path of other significant debris. Currently, 5 celestial bodies are officially recognized as dwarf planets: Ceres, Pluto, Haumea, Makemake, and Eris. The distinction emphasizes that while they are substantial, gravitationally dominant bodies in their immediate vicinity, they are part of a larger population of similar objects in their orbital zones. Ceres, the asteroid belt's largest resident. Ceres, named after the Roman goddess of agriculture, is unique among the dwarf planets, as it is the only one located in the main asteroid belt. Discovered in 1801 by Giuseppe Piazzi, it was initially classified as a planet, then an asteroid, and finally reclassified as a dwarf planet in 2006. With a diameter of approximately 940 kilometers (585 miles), Ceres is the largest object in the asteroid belt, accounting for about a quarter of its total mass. Its spherical shape, confirmed by the Dawn spacecraft, is a clear indication that it has sufficient mass for its own gravity to pull it into hydrostatic equilibrium. Ceres is of immense scientific interest because it is believed to contain a significant amount of water ice, possibly even a subsurface ocean. Data from the Dawn mission, which orbited Ceres from 2015 to 2018, revealed evidence of water-bearing minerals, hydrated salts, and even cryovolcanic activity, where briny water erupts onto the surface. The presence of bright spots within some craters, notably Akata crater, are thought to be salt deposits left behind by evaporating brines, suggesting recent geological activity involving water. Ceres' low density also supports the idea of a substantial ice content, perhaps making up 25–30% of its mass. Its composition, including ammonia-rich clays, suggests it formed in the colder outer solar system before migrating inwards. Ceres is considered a prime target in the search for extraterrestrial life, as the combination of water, minerals, and internal heat could potentially create conditions suitable for microbial life, even if only in a subsurface ocean. The study of Ceres provides a window into the early solar system and the potential for water-rich bodies in unexpected places. Pluto, the iconic king of the Kuiper Belt. Pluto, named after the Roman god of the underworld, was discovered in 1930 by Clyde Tombaugh and was considered the ninth planet for 76 years. Its reclassification as a dwarf planet in 2006 sparked considerable public debate, but was a scientifically necessary step, given the discovery of numerous other large icy bodies in its orbital region. Pluto resides in the Kuiper Belt, a vast ring of icy bodies extending from about 30 to 50 astronomical units from the Sun, a region that will be discussed in more detail in a later part. Pluto's average distance from the Sun is about 39.5 astronomical units, but its orbit is highly eccentric and inclined relative to the ecliptic plane, occasionally bringing it closer to the Sun than Neptune. The most comprehensive understanding of Pluto came from NASA's New Horizons mission, which performed a historic flyby in July 2015, providing the first close-up images and scientific data of this distant world. These images revealed a surprisingly complex and geologically active world, far from the inert ice ball many had imagined. Pluto's surface is a diverse landscape of mountains, plains, and glaciers, primarily composed of nitrogen, methane, and carbon monoxide ices. The most famous feature is the large heart-shaped region informally named Tombaugh Regio, particularly its western lobe, Sputnik Planitia, which is a vast, smooth plain of nitrogen ice. This plain shows evidence of convection cells, suggesting the nitrogen ice is slowly flowing, similar to glaciers on Earth. Pluto also exhibits evidence of cryovolcanism, where volatile materials like water, ammonia, and methane erupt onto the surface as icy lavas. Features like Wright Mons and Piccard Mons are thought to be cryovolcanoes. The presence of relatively few impact craters in Sputnik Planitia indicates that this region is geologically young, suggesting ongoing resurfacing processes. This geological activity is surprising for such a small distant body, and is thought to be powered by residual heat from its formation, and possibly tidal heating from its largest moon. Pluto has 5 known moons, the largest and most significant being Charon. Charon is so large, about half the diameter of Pluto, that the two bodies are often considered a binary system, orbiting a common center of mass barycenter that lies outside Pluto's surface. Pluto and Charon are tidally locked to each other, always showing the same face. The other 4 moons, Styx, Nix, Kerberos, and Hydra, are much smaller and irregularly shaped. The New Horizons mission also revealed a thin, hazy atmosphere around Pluto, composed primarily of nitrogen, methane, and carbon monoxide. This atmosphere expands when Pluto is closer to the Sun and contracts as it moves further away, freezing onto the surface. The reclassification of Pluto as a dwarf planet, while initially controversial, has helped to refine our understanding of planetary systems and the diversity of objects within them. It highlights that the solar system contains not just a few large planets, but also vast populations of smaller, yet scientifically fascinating, bodies that provide crucial clues about its formation and evolution. The exploration of Ceres and Pluto, once distant points of light, has transformed them into complex, dynamic worlds, challenging our preconceptions and deepening our appreciation for the intricate wonders of our cosmic neighborhood. The study of these dwarf planets continues to push the boundaries of our knowledge, revealing the surprising geological activity and potential for water-rich environments in the outer reaches of the solar system.